Contingency tables or cross-tabulation tables categorize two categorical variables based on observed counts or frequencies in each of several categories. For example, 1. Course letter grade and gender. 2. Political affiliation and support or non-support for a candidate. Number 3. State of birth and political affiliation. Or number 4. College major and plans for highest degree, bachelor's, master's, or PhD. The question really is whether there's evidence that the two variables are dependent. So the hypotheses are h sub 0, the variables are independent, h sub a, the variables are dependent. Basically, dependent means that if you know the category for one of the variables, it changes your belief about the likelihood or chance of being in a specific category for the other variable. Example, consider state of birth and political affiliation. Not knowing anything about a randomly selected American citizen, what's the chance the person is a Republican? You might say the value is around 45%, for example. Number 2. Dr. Miller is from South Carolina, lived there for 31 years growing up. What do you think his political affiliation might be? Now, knowing he's from South Carolina, where the state has voted for the Republican presidential candidate for several decades, it seems he's more likely to be a Republican. So perhaps now, knowing the person is from South Carolina, you might say 60% chance of being Republican. Now, in this case, knowing the state of origin changes your belief about being Republican. That would be dependent. And to satisfy your curiosity, I'm actually registered as an independent and have voted for candidates in both parties. Consider another example. Suppose a random sample of students who were categorized by favorite subject area and gender was collected. What is meant by independence? Basically, is the percentage the same for each group? An example of independence might be the following table. Notice the counts are different because there were 200 females but only 100 males. So you can't directly compare the frequencies, but looking at percent in each subject among the males and percent in each subject among the females, the percentages are actually identical. So knowing gender doesn't impact which subject is selected as the favorite subject area. Notice although there were 40 males who said social science was their favorite subject and 80 females who said the same, the percentages are actually both 40%. So the percentages put the values on a comparable scale. Now let's look at an example that's not made up and quite so simple to figure out and see how we would answer the question in general. In this example, there were 122 males and 178 females. The percentages are again based on the total number of each gender. For males, 37 of the 122 chose math or science, so that's about 30%. Similarly, 41 males is 34% choosing social science, with the remaining 36% selecting the humanities as their favorite subject area. Going through the same calculations for the females, 35 of the 178 females is 20% who chose math or science, 72 of the 178 represents 40% who chose the social sciences, and the remaining 71, again yielding 40%, selected the humanities as their favorite subject area. Now the percentages were calculated based on the row totals, the 122 males and the 178 females. It's not always based on row totals though. It depends on which variable you select to create the percentages. Since the percentages were calculated based on each row, the comparisons are made among the column percent values. So you would compare the 30% to the 20% under math and science, the 34% and the 40% under the social science area, and the 36 and 40% under the humanities area. But let's talk about the idea of independent and what it represents in terms of probability. If event A and event B are independent, which is the assumption under the null hypothesis, then the probability of the compound event, written A and B, denoted as P parentheses A and B, is simply the product of the two individual probabilities, the probability of A times the probability of B, or P parentheses A times P parentheses B. Assume that gender and favorite subject area really are independent. So if event A is the person is male and event B is the person chooses social science, then the probability of person randomly selected from the 300 turns out to be a person who is male and the person prefers social science, denoted as P parentheses person is male who prefers social science, would simply equal the product when multiplying. So in notation we would just write the probability P, the person is male, times the probability P parentheses person prefers social science. Now what is the probability a randomly selected person is just male? Well, out of 300 people there were 122 males, so the probability the person is male is just 122 divided by 300. Similarly, the probability a randomly selected person from the 300 prefers social science would be the 113 who did that out of 300. So the probability any one randomly selected person is a male who also prefers social science, if the events are independent, would just be the product of those two values, 122 divided by 300 times 113 times 300, which equals 13,786 over 90,000. Now if we wanted to place the 300 people in the table randomly, we would simply take the number of people, the 300, and multiply by the probability of being in any single position in the table. This is called the expected cell count. Think of rolling a six-sided die 30 times. If each value 1 through 6 is equally likely, a 1/6 chance, then you expect 1/6 of the 30 rolls, or 5 rolls, to produce a 1, 5 of the rolls to produce a 2, 5 of the rolls to produce a 3, and so on. Or think about flipping a fair coin 20 times. You would expect to see 10 heads and 10 tails. But that's simply because you think of the chance of getting a head as a half times the number of flips, 20. And half of 20 is 10 heads and 10 tails. So how many people would we expect to be male social science favorite subject area people if the variables are independent? Well, it would just be the 122 over 300 times 113 over 300 for that probability we found times the number of times we're going to do this, and we're putting 300 people in, so multiply by 300. And notice this simplifies to be just the 122 times 113 over 1/300. Okay, and that gives you 45.95, and that's an average. So if this study were done over and over a bunch of different times, then what we're saying is that the average number in the male social science location in the table we expect to be 45.95. So in short, if gender and favorite subject area are independent, then the expected cell frequency is just going to be your row total multiplied by the column total and then divided by the number in the sample. So how many do we expect in the male social science category? We could get that as just 122 for the row total for males times 113, so that's the column total for social science, equals 13,786, and then divide that by 300, the sample size, and that would give me 45.95. So we could calculate the expected cell counts for each of the categories, okay, and there's 6 in this example. Just remember, in calculating the expected cell counts, we're making the assumption the two variables being considered are independent. So we're assuming that the null hypothesis is true when we're doing this calculation. So next, we want to compare what we expected to see to how the collected data actually turned out. So if these are similar values, we have no reason to doubt the null hypothesis H0. But if these are very different, we will believe HA instead of HO. Now we can compare the observed cell frequencies to what we expected to see. And if this value is small, there's little reason to doubt the null hypothesis. But if this value is large, this suggests the variables are dependent instead of being independent, and we say there is support for the alternative hypothesis. We have a new test statistic called the ChiSquare test statistic. It's calculated using the formula ChiSquare equals observed count minus expected count squared divided by the expected count, and then we add that up for all 6 of the cells in our example, or in more generality, for all the cells in the cross tabulation table. This has a chi-square distribution with what is called degrees of freedom, written df, which equals r minus 1 times c minus 1, where the values are just that r is the number of rows in your table, not including the total, and c is the number of columns in the table, again, not including the total column. Now this is going to be valid when all of your expected cell frequencies are at least 5. Okay, so that's going to be your validity check along with taking a random or representative sample. The expected cell frequencies are listed below the observed counts in the table below. We can actually calculate these values ourselves or use software like StatCrunch to find the expected values. You should be able to do this with the row total times column total divided by sample size formula pretty quickly. So let's calculate the test statistic using our formula. So for example, with the male math science category, 37 was the observed count minus the expected count of 29.28. We square that and then divide by the 29.28 plus, move over to the right, 41 minus 45.95 squared over 45.95, and so on. So we do that for each of the 6 cells, and we get a final calculated value of about 4.60575 if I put it all in the calculator and do it all at once using these numbers. Sometimes we'll use StatCrunch to perform the calculations. So what you do is enter the table into StatCrunch just like you would in a spreadsheet, and then you use the stat tables contingency with summary commands. Enter the columns that have the table, not the first column that has your like gender, but the ones that have the actual counts. Then you tell it which one the row labels are in. So that's what you would tell it. The gender column has the male and female designation. And then you can click display, or under this display tell it to go ahead and show you the expected count, and then click compute. And the next slide has the table with the expected cell counts and test statistic. We're going to focus mainly on the expected cell counts to make sure they're all 5 or more so that our analysis is valid. And then we're going to look at the chi-square test statistic value and the probability, or the p-value. And remember, if this is less than our level of significance alpha, we would reject the null hypothesis. Notice the table matches what we produced doing the hand calculations earlier. The test statistic matches when you round to 3 digits after the decimal point. Round off error in our own calculations when we got the expected cell counts is what causes the slight difference. Let's look at a quick summary. First, note that we assume a random sample is collected, but we see that all the expected cell frequencies, the numbers that are in parentheses, are greater than 5, so the method is valid. Also, the test statistics value is that chi-square is 4.606, and the probability, or the p-value, is 0.0999. We would fail to reject the null hypothesis for an alpha level of 0.05. We conclude there's insufficient or insignificant evidence at a 0.05 level that gender and favorite subject area are dependent. This implies the sample percentages would be similar for major regardless of gender. So any differences in the percentages earlier were not strong enough to suggest or support a difference based on gender when looking at favorite subject area. Let's calculate the sample percentages. So the question will be stated as follows. For each gender, calculate the percentage for each favorite subject area. So we'll start with males. So for all the males, the 122, how many were in each favorite subject area? And then make that a percentage. So 37 divided by 122 times 100 is 30.3% of males indicated math or science as their favorite subject. 41 divided by 122 is 33.6% who indicated social science, and 44 divided by 122 times 100 is 36.1% who indicated humanities. Now consider the females. So for all 178 females, how many were in each favorite subject area? 35 divided by 178 times 100 gives 19.7% of females who indicated math or science. 72 divided by 178 times 100 is 40.4% of females who indicated social science. And 71 divided by 178 is 39.9% of females who indicated humanities. So the table with the percent values inserted for the rows looks like the following. Now since we calculated the percentages based on the row totals, so out of all males give the totals and out of all females give the totals, we're going to compare the percent values in each column. So compare to see how similar or different are the 30.3% and 19.7%, the 33.6% and 40.4%, and the 36.1 and 39.9%. As a rule of thumb, we're looking to see if the percentages are more than 10% different, or are they 10% or less different. Okay, and this is just a rule of thumb. It really depends on the sample sizes and everything, but it doesn't always work perfectly. Okay, but let's examine our three pairs. So 30.3 and 19.7% are a little more than 10% different. Now the 33.6 and 40.4% and the 36.1 and 39.9% are less than 10% different. So the first comparison seems to indicate there might be a dependent relationship, but the other two comparisons suggest that there might not be a dependent relationship. Recall the p-value is 0.0999, and that would be less than an alpha level of 0.10, but it's not enough evidence if we set alpha at 0.05. Okay, and since we set alpha at 0.05 earlier, we would have concluded there's not significant evidence of a dependent relationship. So this concludes the ChiSquare example.